You should have gone over some exercises so you can recognize and write a fission reaction. But let me just review for a minute. A fission reaction is a type of nuclear change in which a target nucleus is bombarded by a neutron with a relative amount of kinetic energy, and that unstable nucleus then splits apart into what's called fission products, two fission products, and normally 2 or 3 neutrons as well. The fission products are usually of nearly equal size. So that's how we can recognize a fission reaction. Let me show you a quick animation of that. Here you see the neutron coming in, colliding with the uranium-235 nucleus and producing 2 fission products and 3 neutrons. Now the 3 neutrons are now able to go ahead and collide with another nucleus, uranium-235 nucleus, which is why this is referred to as a chain reaction. We'll talk more about that in the next video. So nuclear fission was first published in Nature in 1939, and the term fission was taken from biology because the scientists had already seen that cells can undergo fission, split into 2, and so here they're showing that nuclei can split into 2. And it was also found that energy was given off upon a fission reaction. Heat energy was also given off. Okay, heat energy given off in a fission reaction. And as it turns out, the source of that heat energy had been predicted already by Einstein in his famous theory of relativity. He had said that matter and energy are interconverted via this reaction. E energy equals m mass times c, and c is the speed of light. And here it's squared. All right, so this is Einstein's famous equation, and he had hypothesized that this was that energy and matter were interconvertible a decade before nuclear fission had been observed. Okay, so now when we were learning about fission reactions, we learned that you can balance fission reactions because the mass number and the nuclear charge are conserved. So this business about matter converted to energy is just crazy. It goes against everything that we've learned, and that is that matter is conserved. But as it turns out, matter and energy are interconverted. Now if you look at this fission reaction that we've studied already, you can see by adding up the mass numbers on the reactant sides is equal to the mass numbers on the product side. So mass number is conserved, and also nuclear charge across the bottom. The left-hand side is equal to the right-hand side. So nuclear charge and mass number are conserved. But when you take a closer look at the mass of all of the nuclides and the particles, nucleons, the particles within the nuclides, you can see that there is a difference between the left-hand side and the right-hand side of these equations. This one's pretty complicated, so let's look at a simpler example so I can prove this point to you. In this case, this is just a neutron decaying into a proton and an electron. In this case, this electron would be fast moving, so it would be referred to as a beta particle. Okay, and if you look at the actual masses of each one of these particles, then out to several significant figures, masses, not atomic mass numbers or units, but actual kilogram masses. The neutron, the mass of a neutron is 1.6749272 times 10 to the negative 27 kilograms. Okay, that's the mass of a neutron. A proton, the mass of a proton is 1.672616 times 10 to the negative 27th kilograms. And a tiny little electron, the mass of an electron is 9.01938 19 times 10 to the negative 31 kilograms. Okay, and so if you look just at the neutron versus the proton, a neutron out to the first 1, 2, 3, 4, 5 significant digits, you see that the neutron, actually you only have to go out to 4 significant digits to see that the neutron 7.4 versus 7.2 is heavier, than the proton. And even when you add the mass of the electron to the mass of the proton, that sum is still less than the total for the neutron. As it turns out, if you look at the mass difference, the difference in mass across this nuclear change, which would be the mass of the final, the proton plus the electron, minus the mass of the initial thing, which is the neutron, that mass difference is, final minus initial, is going to be negative 1.3947 times 10 to the negative 30 kilograms. So you see that the mass difference is a negative difference, which means that there's less mass on the right-hand side than the left-hand side. So what happens to that mass? It doesn't just disappear. That mass is converted to energy. Okay, so the energy is released across these nuclear changes because the sum of the masses of the fragments is less than the sum of the original mass. And normally, the missing mass is about 0.1% of the original mass in these nuclear changes. Okay, so a small amount of mass is always going to be converted to kinetic energy and carried off by the products of the reaction. So in the example that I just showed you with the neutron being converted to a proton plus an electron, let me put in all of this proper notation. When the neutron is converted to the proton, there's kinetic energy that's also given off. So some of the mass is literally being converted into energy. All right. So given this information, it's a relatively simple equation. You can actually calculate the amount of energy that should be given off when 1 kilogram of uranium-235 undergoes fusion. Okay, now remember, the amount, the estimate that we use is that the amount of the fuel that actually gets converted to energy is about 0.1%. Okay, so 0.1%. So we can calculate the amount of energy given off across a nuclear change by modifying our equation slightly to say the change in energy across the nuclear change equals the change in mass across the nuclear change times the speed of light squared. So in this case, the change in mass, if we had, let's see, what we say here, 1 kilogram of uranium-235, the change in mass is going to equal 0.1%, 0.1% times the initial amount, which is 1 kilogram. And 0.1%, as you know, is the same as 0.001 times 1 kilogram is equal to 0.001 kilograms. So our delta M there is 0.001 kilograms, and it's negative because the final is less than the initial. So to calculate the energy, it's going to be delta M equals negative 0.001 kilograms times the speed of light squared, and the speed of light, as we said previously, is 3 times 10 to the 8th meters per second squared, which would be the same as 9 times 10 to the 16th meters squared second squared. And so the change in the energy here is going to be negative 9 times 10 to the negative 13, excuse me, not negative 13, my bad, 9 times 10 to the 13 kilograms meters squared second squared. That might look like a strange unit, kilograms times meters squared divided by second squared, but that's actually the same as the energy unit, the joule. So it's negative 9 times 10 to the 13 joules. And the negative indicates that heat is given off. That's our convention. Heat's given off. You may remember that from your high school chemistry class. We call that exothermic. So it's just indicating the direction of the energy change. Heat is given off. All right, so the amount of heat energy that's given off is 9 times 10 to the 13 joules. All right, how much heat energy is that for just 1 kilogram of uranium-235? Well, TNT is trinitrotoluene, discovered in 1863 by Alfred Nobel. That's dynamite. dynamite, 1 kilogram of uranium-235, where only about 0.1% of the mass is converted to energy, is equivalent to 33,000 tons of TNT. Okay, that's several dump trucks full of TNT going off at the same time. So you can see just 1 kilogram of uranium-235 gives the same as 33,000 tons of dynamite. That's a lot of heat energy given off. So this, in summary, from this little video, you should be able to recognize a fission reaction. You should understand that the heat energy given off is due to a conversion of a small amount, about 0.1% of the mass, into energy, and you ought to be able to calculate the amount of heat energy given off upon a nuclear fission reaction. And you'll have some homework problems to practice doing that.